Hello, everybody. My name's Joseph Tanner Slagle. It's a beautiful day in Virginia. I hope everyone is doing well. Thanks for tuning in to this talk about formal verification of semi-algebraic sets and real analytic functions. This talk is for CPP 2021. I want to thank the organizers, Dr. Popescu and Dr. Hredku. They've done an awesome job communicating over the past months. I hope we can all meet in the physical realm one day. For now, I guess we will just continue talking virtually. So, I'm here to talk to you about some research I did with a couple colleagues this last summer. Lauren White was my intern. She is finishing her PhD in mathematics at Kansas State, and Aaron Duddle is another civil servant in the formal methods group at NASA Langley. So, let's go ahead and start. Let's talk about some motivation for this project. So the motivation for formal verification of semi-algebraic sets and real analytic functions comes from the need to reason about hybrid systems within PVS, or to formally verify safety properties of hybrid systems. So a hybrid system is a system that has both discrete and continuous variables. Normally the continuous variables, or perhaps maybe not normally, but the continuous variables can be described as the solution to a differential equation moving through time. I think a basic example is perhaps an aircraft represented by the solution to a differential equation, and then a geofence, which is described by some semi-algebraic set. So the idea is that hybrid systems are very useful because they can describe a lot of different systems, and they can describe a lot of very complex cyber physical systems. These systems often have a safety critical component to them, so it's important that properties of these systems are formally verified. So differential dynamic logic is a formal logic for specifying and verifying hybrid systems. So our goal is to implement DDL in the prototype verification system, which is a formal specification and verification language. The thing is that DDL is not a trivial logic. It requires a lot of reasoning about mathematical objects, in particular multivariate polynomials and semi-algebraic sets, as well as real analytic functions, and then also the way that a real analytic function might behave around the boundary of a semi-algebraic set. So if we assume the solution to this differential equation is a real analytic function, then we might be curious how the real analytic function leaves and enters the semi-algebraic set over time. So you'll see right here, this is what I like to call a clean exit. So it's in the semi-algebraic set, but then the real analytic function breaks out of it, and it's entirely on the outside of this semi-algebraic set. There's no weird infinite oscillations around the boundary. The behavior is pretty nice. So this is a very fundamental property. If you think about it in terms of a plane flying in and out of a geofence, I think it's a property we would all expect to be true. And the idea is that with these mathematical objects, you also want this fundamental property to be true, because that in a way validates reasoning about these things using semi-algebraic sets and real analytic functions. Okay, so hopefully I've motivated this enough for you. Now that I've motivated it, I'm going to walk through the different formalizations we did. I'm going to start by talking about semi-algebraic sets, and then we're going to move on to real analytic functions, and then we're going to talk about how real analytic functions behave in and around the boundary of semi-algebraic sets. Then, of course, we'll wrap up with conclusions and future work. Let's talk about a multivariate polynomial. To construct a general multivariate polynomial, you start with a primitive monomial, and it's denoted with this boldface x raised to alpha. Now, alpha is a vector that corresponds to the exponents used for each of the separate variables. So you see this monomial is in m variables, and they're denoted x sub 0 all the way up to x sub m minus 1. and each one of them is raised to a different power. So you can imagine a primitive monomial is just all the variables you're considering multiplied together raised to certain degrees. You'll notice that these degrees are in the natural numbers, so 0 is very much allowed here. Great. So then a monomial is nothing more than a primitive monomial, but you multiply it by some real scalar. And then to get the multivariate polynomial, you take a bunch of monomials and you create a linear combination of them. So a multivariate polynomial is just the sum of a bunch of different monomials. All right, so this is what multivariate polynomials look like mathematically. This is how we implemented it in PVS. The monomial is a record data type, and it has two fields. One field is the scalar multiple in front of the variables, and then the other field we call alpha, and it is a list of natural numbers corresponding to the degrees of each variable in the monomial. A particular instantiation of this monomial would look like this. Here, C is an actual real number, and L is a list of natural numbers. To access a certain particular field, we use this dash or apostrophe. So M dash alpha is L. So once you have monomials in PVS, you can create a multivariate polynomial by simply just creating a list of monomials. So an instantiation of this would look like this. Here's an example, P1. This is a list that has two entries. Each of the entries is a monomial. The first monomial, if we call the one variable being used x, this is x squared. And then the second monomial is x. So P1 is x squared plus x. So you can have many polynomials. I've written polynomials here that are syntactically different, but they evaluate to the same value when given any variable values. I've written these polynomials over here in the PVS syntax. You'll notice takes up a little more space. But we need some way of talking about a polynomial uniquely. And when I say unique, I mean unique in the sense of evaluation, or when we consider these polynomials as functions. So all 5 of these polynomials right here are the same in the sense of evaluation, yet they are syntactically different and can be written as such in PVS. So to create a unique representation of polynomials, we're going to develop the notion of standard form. So a polynomial in PVS is in standard form when each one of these predicates are satisfied. So the lifted predicate enforces that each alpha list in every monomial in a multivariate polynomial is the same length, and that the last variable in the list is used in one of those monomials. So this is essentially saying that the polynomial is written in the least dimensional space it can be written in, but all the monomials are written in that dimension. Now simplify enforces that each alpha is used at most once in a multivariate polynomial. For example, you can have two monomials associated with x squared. The x squared term can only appear once in the multivariate polynomial. All non-zero enforces that each of the scalars in front of the monomials are not zero. This enforces that the zero polynomial is the null list. And then finally, the monomials that appear in a list must be sorted in some way. There are a lot of different ways to sort monomial terms. We chose graded lexicographical order. And to talk about graded lexicographical order a little bit, what that means, it's a total order on monomials, and one monomial is less than the other monomial when one of these two statements is true. The first one is that the overall degree of the first monomial is less than the overall degree of the second one. And then the slightly more fringe case, perhaps, not really a fringe case, is that the degrees of the monomials are the same, but the earliest differing exponent is smaller in the first monomial. So here's an example, illustrative example. You have these four monomials. They are in graded lexicographical order. So you'll notice that this first monomial has degree 2. Therefore, it is less than the rest of these three monomials because each one of them has degree 4. Now, these middle two, this second one is less than the third one because the exponent corresponding to x1 is raised to the first power, whereas x1 is raised to the second power here. So this is less than this. And then finally, x0 to the fourth is the greatest monomial because it has the highest exponent of the very first variable. So let's look at an example of standard form. I talked about the predicates, but with each predicate, maybe you saw there is actually a transformation that inherits a polynomial with the desired predicate. So let's look at this. So I have this multivariate polynomial. The first thing I do is lift the multivariate polynomial so that each monomial is existing in the same dimension, but also that that dimension is not redundant, right? So x2 is actually being used in two of these monomials, so it made sense to lift the middle two monomials. So after you lift the multivariate polynomial, then you sort it according to graded lexicographical order, and then you simplify. So to simplify, I believe these first two monomials had the same variables with the same degrees. Therefore, we could put them together and simplify them. So once you do the lift, the sort, the simplify, the all non-zero, which was not necessary in this example, you get a polynomial that is in standard form. This polynomial is in standard form. Showing that it was actually in standard form required a lot of lemmas that sort of showed that if a bunch of these properties sort of carried through these transformations. For example, if you lift a polynomial, then you sort it, is it still lifted? Another example is if you lift a polynomial, then sort it, then get rid of all the zero coefficients, is that still sorted? So you can imagine that there were a host of these things we had to prove in PVS. They are something I think that we would all accept to be true if we thought about it a little. But of course, it was a little more involved to prove those things in PVS. So once we have defined standard form, we have the property that standard form gives you a unique polynomial up to evaluation. So if you have a function, sigma, that returns the standard form of a polynomial, and the standard form of two polynomials is equal, or the standard form of two polynomials being equal is equivalent to them evaluating to the same value for every single input. In PVS, this theorem looks like this. So you see the MV standard form function. This is what takes a multivariate polynomial P and creates a polynomial in standard form. And then full eval is the evaluation function in PVS. All right, let's move on to semi-algebraic sets. So to construct a semi-algebraic set, you start with the atomic polynomial formula, which is using some inequality to relate a multivariate polynomial to 0. So when you plug in a particular value for the variables in the multivariate polynomial, an atomic polynomial formula will return either true or false. So you take a bunch of atomic polynomial formulas and you construct a disjunction of conjunctions of those atomic polynomial formulas, and this is called a quantifier-free polynomial formula. You'll notice that the way we've specified it here, it is already in disjunctive normal form. That is also how we will implement it in PVS. So once you have a quantifier-free polynomial formula, a semi-algebraic set is nothing more than the set of all the values, all the particular real values, that when you plug it in, to this quantifier-free polynomial formula, you get true. Great. So in PVS, we defined the atomic polynomial as a record type, and the record type has a polynomial element or field and an inequality field. The inequality is less than or equal to, greater than or equal to, greater than or less than. I should note that we could have included equals and not equals, but doing it this way does not reduce the expressiveness of what we can, what sort of semi-algebraic sets we can express. So then to construct the quantifier-free polynomial formula, the inside conjunction is a meeting, and a meeting is a list of atomic polynomial formulas. And then to describe a disjunction of all these conjunctions, a joining is a list of a bunch of meetings. So here we have a disjunction of two conjunctions. In PVS, this would just be a list of lists. So it's a list. The first entry of the list corresponding to the first conjunction is AB. The second list in the list is CD. This corresponds to the conjunction CD. And each one of these entries is connected with a disjunction. And that corresponds to the outermost list. So you'll notice that this has a direct correspondence with disjunctive normal form. Once you have that in PVS, defining a semi-algebraic set is nothing more than constructing the set such that the set of all the vectors that satisfy that joining expression. So once we put semi-algebraic sets in PVS, there was a lot of properties we could prove. This property is that the union of two semi-algebraic sets is a semi-algebraic set, the intersection is a semi-algebraic set, and the complement is a semi-algebraic set. So these are, when you think about these, they're quite straightforward, even to prove, I think, on a pencil and paper. But because we define semi-algebraic sets using the disjunctive normal form of the joining expression, there's a little bit of subtlety I'd like to talk about. So the disjunction of two joining expressions, that's the easy case. All you do is you take two joining expressions and you concatenate those lists and you get one big joining expression. It's already in disjunctive normal form. It is the disjunction of a bunch of conjunctions, so you're done. Now, the conjunction of two joining expressions requires a little more finesse. It requires, because you have two joining expressions, you have to have the ability to distribute a conjunction across many disjunctions. Once you have this, getting the complement is relatively easy. You just need to flip the inequality in each of the atomic polynomial formulas, and then you need to swap the conjunction and the disjunction. And that really boils down. Once you have the conjunctive case, it's not too bad to get that case. I want to talk about the conjunction case a little. This is the case where you are transforming the conjunction of a joining expression with one atomic polynomial. So you have one atomic polynomial, you're conjuncting it with something in disjunctive normal form. You want to write it again in disjunctive normal form, and you can. What it really boils down to is taking this atomic polynomial formula and putting it inside this conjunction, adding it to each of the conjunctions at the very end. You're essentially appending that atomic polynomial formula to each of those conjunctions. Once you have that, you can actually use this repeatedly to find the disjunctive normal form of the conjunction of two joining expressions. And you'll see that this append to each function is exactly what this is doing. And then you just repeat that, and you're recursing on J1. So you're using the first entry of J1, distributing it across all the conjunctions, and then you move on to the rest of the list. So once you have this function showing that the conjunction of two semi-algebraic sets is a semi-algebraic set is relatively easy. All right, let's move on to real analytic functions. So I'm sure you've heard of analytic functions in complex analysis. These are extremely powerful objects that are equivalent to being differentiable, equivalent to being integrable, equivalent to being holomorphic, and you can do a ton of fun stuff with them. Real analytic has a similar basic definition, but because the function is real valued, you don't get as many of these nice equivalencies because things just don't work out as well for real valued functions. So the definition is f is real analytic at a point c sub 0 if there is some real sequence, ak, and some radius of convergence r, such that f equals the power series made with the sequence ak in a neighborhood, in that R neighborhood around the point C0. So what it's basically saying is that f of x is equals some power series in some neighborhood around the point that it's real analytic at. So you'll notice that the sequence AK and the radius of convergence R are the real stars of this definition. So the way that we implemented this in PVS was we created a predicate on those two quantities called analytic parts. You have a C0, you have F, and then R and AK are analytic parts if F is equal to the power series in the R neighborhood around C0 that's made with the sequence AK. So once you have the analytic parts definition, to make a function analytic, you just say f is analytic when there exists some positive real number r and a sequence ak such that they are analytic parts of f, I guess. So just like semi-algebraic sets, there's a bunch of basic things you can prove about real analytic functions. Here are some we proved. The sum of two analytic functions is analytic. This just follows from properties of infinite series, which were already actually in the NASA library of PVS, as well as the constant multiple of analytic function is analytic. That also followed from these properties. The really difficult one actually was the product of two analytic functions is analytic. This was not a trivial thing to prove. So first you actually have to find the form of this product, and you have to use this discrete convolution operator that sort of convolutes the sequence associated with f and g. It's important to note, if you have two series and you make a new series by multiplying the terms of these series, that need not converge necessarily. The reason the product of two analytic functions converges is because if a function is analytic, the series that it equals to is actually absolutely convergent in that neighborhood around C0. So you have to use absolute convergent to get the convergence of this series. Really interesting proof. I had a lot of fun with it. And then, of course, once you have all this, you can say a non-negative power of an analytic function is analytic. The reason I included this last point is because we're going to need this property to show when you compose a polynomial with a real analytic function, you get a analytic function back, which is going to be essential for the next section. I want to just make this note that smooth and analytic are not the same thing. I think this is something that they talk about in undergraduate real analysis class, but let's just hammer it home again because it's going to come up later. So analytic is stronger than smooth. If you take this function Sm, it's called Sm because it is a smooth function. You can show that the nth derivative takes this form. It's some big quotient where this Pn of x and Qn of x are polynomials. And the derivative is that for a positive x and then it's 0 elsewhere. But it is not analytic. Before I get to analytic, I want to point out that proving this in PVS required some hoops to jump through. Not just showing this form, but to show that this has a derivative at 0, you have to show that the limit of this monster right here goes to 0. Now, the normal way people would do this is use L'Hopital's rule. L'Hopital's rule. But L'Hopital's rule is not a trivial result. Even though we love to use it, it is not a trivial result to prove, and it isn't in the NASA library for PVS. So we had to find another approach to show that this limit was 0. It turns out that you don't need something as powerful as L'Hopital's rule. You just need some basic properties related to the mean value theorem and derivatives. Really fun proof there. So SM is smooth, but it isn't analytic at 0. And the reason it's not analytic is if there was some M where SM was equal to this power series around 0, this power series would be 0 because SMK at 0 is 0. However, it is easy to see that Sm of x is not 0 in any ball around 0. E to the negative 1 over x sine of 1 over x, you can find points such that Sm is not 0. And of course, we had to find these points in PVS to verify that it wasn't 0. So let's talk about the formalization of real analytic functions with SA sets. So we've described SA sets, we've described real analytic functions. Let's talk about the real analytic functions and how they behave on the boundary of semi-algebraic sets. Then, of course, I'm going to go back to the smoothness issue. It's going to be a good time. So the basic result that we have really follows from this. And it was a whole lot of induction in PVS, but it's essentially saying that if you have an analytic function and you compose it with a polynomial, then the composition of that polynomial and that real analytic function is real analytic. If you think about the properties of real analytic that we did earlier, the product of real analytic functions is real analytic. When you raise it to a power, when you multiply it by a constant, it's all still real analytic. So proving this lemma really was just using those properties as well as induction in PVS. So you start with a monomial, you compose it with a real analytic function, and you just use this recursion. So here you have a real valued function composed with a monomial times, or actually, sorry, you have a real analytic function composed with a monomial of a smaller overall dimension, and then you have a real analytic function raised to a power multiplied by a constant. This is analytic by the inductive hypothesis, and so the product of them is also analytic. Yeah, very good. So it was really induction to show the monomial composed with real analytic was real analytic, and as well as the polynomial, the general multivariate polynomial. So once you have this property, we can characterize the way that a real analytic function behaves around the boundary of an SA set. And to characterize this, we have this theorem. It's called clean exit. There's one for the way that a function might enter as well. But the idea is that if you have this function and it starts inside this semi-algebraic set, then one of these three things is true. Either the function stays in the set forever. That's the boring case, just hanging out in the semi-algebraic set. I guess in the case of an aircraft in a semi-algebraic set, you might want this if you don't want it to escape the geofence it's in. The other two cases are talking about what happens when the function leaves the semi-algebraic set. So if you take x star to be the infimum of all the moments that f is not in the semi-algebraic set, if f is not in the semi-algebraic set at that inf, so in other words, you can replace the inf with a min, then there is some epsilon such that f is in the semi-algebraic set for all moments directly after x sub star. So this is the situation where a semi-algebraic set goes to the or where a real analytic function goes to the boundary of a semi-algebraic set, and then it basically just bumps off the boundary and it goes back in the semi-algebraic set. This last case is when it actually exits. So it goes to the boundary, and then after that, there is some epsilon where f is outside of the semi-algebraic set completely for all moments of time between 0 and epsilon. So this is written in a bit of a confusing way. I mean, because this is how to write this property mathematically requires this sort of footwork. But intuitively, this is probably something that you accepted about, I mean, real analytic functions or maybe functions in general before now. But it's not true for functions in general. So it's possible for this function f, if it was not real analytic, to get to the boundary of S. And then once it hits this boundary S, there's some crazy accumulation of roots of, I shouldn't say roots, of instances where f crosses inside and outside of S, and that first breakpoint is just the limit of all those crazy points. And it's sort of this infinite oscillation. This is what the clean exit theorem is saying. It's saying, all right, well, you have this is, I guess, case 3, I should say. You have this real analytic function, and it exits the semi-algebraic set, and it exits for an entire interval of time. Now, the clean enter theorem that I didn't include in these slides would say that, it goes in, and it's going to remain for some epsilon amount of time. So basically, we're seeing that this real analytic function is just moving in a nice way in and out of this semi-algebraic set. Okay, so analytic is stronger than smooth, and we would want the weakest condition, when formally verifying these things, we want the weakest condition to give us this property that we want about the boundary of the semi-algebraic sets. Smooth is not strong enough. So if you reduce the assumption to smooth, you can come up with a diabolical example where the real analytic function, does not leave the semi-algebraic set in a clean way. In this example, take Sm from earlier. Remember Sm? I said it would come back, and it has. The semi-algebraic set is denoted by this half plane, and Sm is in the semi-algebraic set all the way up to the origin right here. Now the issue is right here, this is the infimum of all the points where Sm of x is outside of S, the semi-algebraic set. The issue is if you look at the top of each of these waves, there's this infinite oscillation happening, and the closer you get to the origin, there are infinitely many of these points that are outside of S. So there's no epsilon neighborhood around this origin here where Sm is entirely inside or entirely outside S. No matter how small you look past this origin, there will always be infinitely many points where Sm is outside of S and Sm is inside of S. This is what that lemma looked like in PBS. It's called not clean exit. We are very creative in the formal methods group with our naming. So what it's saying, all right, well, this infimum of all the points that are not in the semi-algebraic set is 0, right? It's 0. But, well, maybe not but, and there exist two sequences. They both converge to 0. But each of these entries of the sequence for x, the sequence x, all these points are in S. So I'm mainly talking about the bottom points of all these waves. All of them are out. All of them are in, excuse me. And then for y, all of those entries are outside of S. Essentially, this is proving that the smoothness assumption is not strong enough to give us this very fundamental but essential property we're looking for. So we need that real analytic function. We need that real analytic assumption. All right, cool. So let's talk about conclusions in future work. So we formalized this stuff in PBS. We formalized multivariate polynomials, semi-algebraic sets, real analytic functions. There's a lot more to do. So the motivation of this project is to implement DDL in PBS. We are getting close to having the mathematical foundation we need to implement this, but we still need to implement it. And of course, once we implement it, there's a bunch of really cool applications related to aerospace that we can apply, and it's going to be really cool. I should note that there are a lot of other applications for this stuff. So we introduced multivariate polynomials over the real numbers. We could change this formalization for the multivariate polynomials to be defined over an arbitrary ring. That would actually create some more, it would make the specification more robust. So we could definitely prove a wider range of mathematical results. We could also expand the description of semi-algebraic sets in PBS. Right now, we have to put it in disjunctive normal form. It would be nice to actually talk about more general atomic polynomial formulas with conditional statements and if and only ifs, and just have a function that transforms it to disjunctive normal form. And of course, we need the theory of differential equations in PBS still. So I talked about real analytic functions, but there's one small leap we need to make still, that a solution to a differential equation is real analytic. This is a non-trivial step, and we've developed a differential equation library in PBS, but this result still needs to be shown. Thanks for listening. Thanks for watching the video. If you have any questions, please feel free to email me. I think when CPP happens, now we'll have a chance for questions. Oh, but we'll actually be doing the 10-minute video there. So thanks for watching this video. Please feel free to follow up in any way. I really appreciate it. Thanks again to the organizers. I'm really excited to be part of this conference. So thank you.